Okay, so in this next problem, we are also going to be considering the maximization of an area. So reading the problem, we have a farmer with 600 feet of fencing. He wants to construct a rectangular plot for a dog run that he will share a border with his barn. What are the dimensions of the largest dog run that he can build for this situation? What is the maximum area of her dog run? All right, so in drawing this picture, since we're sharing a border with the barn, all right, what that basically means when I draw my dog run, right, that means one of the borders is going to be up against the barn. So we're really actually going to, only use fencing for a couple of the widths and the length, right? So that basically tells us then in terms of work, right, as far as work being shown, right, that basically tells us that our perimeter in this case is just 1L plus 2W, right? And then since we know we have 600 feet of fencing, right, 600 equals L plus 2W. So there, that's a 600 right there. So this becomes our constraint. Of course, what are we trying to maximize? The area, right? And for this case, the area is actually still length times width, right? Even though we're doing that. So the area we have is length times width. So again, like the last problem, here's the function we're trying to maximize, and it actually depends on two different variables. So we would like to, how about get this as a function of W or L, right? Either one's gonna work, right? How about I just do L again like we did up above? So that means I'm gonna come over here, right? And I'm basically going to solve for W. So if I subtract L from both sides, we get that 2W is equal to 600 minus L. Dividing by 2, we get that W is equal to 300 minus, how about I write that as 1/2 L. So I'm now going to take this information and replace this W with that. So L is still what it is, but W is now 300 minus 1/2 L. And if we multiply that out, what we basically get is 300L minus 1/2 L squared. Let me rewrite it this way. Our area as a function of L is negative 1/2 L squared plus 300L. And so there is basically our function for the area. You see that it's quadratic. The lead coefficient is negative, so we do have a quadratic that's opening downwards. So again, to find the maximum area and the dimensions that do that, we're back to finding our vertex. So in this case, our H, our L value that we're going to need is negative B over 2A. And so we get negative 300 over 2 times negative 1/2. And so this becomes negative 300 over negative 1, right? Because 2 times 1/2 is 1. A negative divided by a negative is a positive. So it looks like the length has to be 300 feet. All right, and so we can basically take this amount and come here, right? W, the width that I would have, is 300 minus 1/2 of 300. So this is 300 minus 150, which means that the width would have to be 150 feet. Okay, so we now know the dimensions of this dog run that are going to maximize the area with regard to this situation. What is the maximum area of the dog run? Well, again, you could plug the information here, right? Plug 300 there, or I can just go to my area formula, and the length we need is 300, the width we need is 150, and just do that multiplication there. So off to the side here, 150, how about I do it this way, 300, carry a couple zeros, 3 times 0 is 0, 3 times 5 is 15, carry the 1, looks like what we get is 45,000, and this will be feet squared. Okay, So I think I did my math right there. Yeah, 1, 2, 3, yeah, 45. All right, so yeah, just counting, we have 1, 2, 3 zeros, and then 15 times 3 is 45. So there's basically that area problem. So we're trying to maximize the area of a dog run. I have limited fencing, right? But part of my fencing is not needed since I'm using the side of a barn to form one of my sides. So that impacts the constraint equation, right? We use the constraint equation to help us rewrite our function that we're trying to maximize in terms of one variable. We got lucky, right? Because once we did that, we end up with a quadratic function. And basically doing all the maximization and optimization just requires finding the vertex yet again. All right, so there's another area one. We've got some more different types of problems coming next, but hopefully you guys are seeing how these optimizations problems are done, how useful it is to have a quadratic, and we'll do that in some problems coming soon. Talk to you later.